Hi, everyone. I think we're going to get going now. So thank you for joining and welcome to this joint Geoscience BC and MDRU session on exploring BC's porphyry copper deposits using zircon, apatite, and titanite. My name is Krista Pellet. I'm the Vice President of Minerals at Geoscience BC, and I'm pleased to be speaking to you for today from Kamloops in the traditional territory of the Kamloops to Secwepemc. Joining us here today are Dr. Craig Hart, the former director of MDRU, who's going to be providing us with a short introduction to MDRU following my talk, Dr. Farhad Bouzari, a research associate at MDRU and a respected and leading researcher on porphyry indicator minerals, and our main presenter today. We also have Jean Liu from MDRU, who will be handling questions at the end of this session. And in the background, we have Geoscience BC's Candace Appleby looking after the technology. Before we get started today, a few housekeeping rules to help keep things moving smoothly. Please make sure your microphone is muted. It should be muted by default. Only turn on your mic if you are talking. Please be aware that this session is being recorded and will be available to view on Geoscience BC's YouTube channel in the coming days. Finally, there will be plenty of time for questions at the end. So please insert your questions into the chat as we go, and Jean will run through them at the end. Now, most of you, I think, are probably familiar with Geoscience BC, but for those of you who aren't, Geoscience BC generates independent, relevant public earth science research and data about BC's minerals, energy, and water resources. And this work helps to advance our knowledge of BC's geology, reform responsible development, encourage investment, and stimulate innovation. Geoscience BC has been around since 2005, and since then has complemented the work done by government research agencies and scientists, such as the BC Geological Survey and the BC Oil and Gas Commission on the energy and water side. Geoscience BC's collaboration with resource sectors, academia, communities, Indigenous groups, and governments across the province helps to develop and share unbiased and credible earth science research and data. And for every $1 we've spent on minerals research, an additional $6.60 is invested back into mineral exploration in BC. To date, Geoscience BC has 156 completed and current mineral projects in the province, and results and data for all of our completed projects, as well as papers for some of our ongoing projects, are all available on our website. We've worked with MDRU on a number of projects, including a number of projects that Dr. Bouzari is going to tell us about this morning. Geoscience BC and MDRU have a strong history of working together, so I'm really pleased to pass you over to Craig Hart for a short introduction to MDRU before we hear from Farhad. Craig, over to you.
Great. Thanks a lot, Krista. Yeah, I just want to follow up by starting that the main point is that the MDRU and Geoscience BC have had a great relationship over the last decade or so. And what we're going to hear today is really a fruit of that partnership, where over the last 5 or 6 years, we've been working on ways and means to find improved methods and technologies to help us contribute to exploring through cover. We all know the problems in dealing with cover, and sometimes sampling is difficult, the geochemistry is difficult, but we find that the mineral grains themselves provide a tremendous amount of insight in terms of contributing to decision making. And this is a sort of project that we do really well. Is MDRU is essentially formed to provide a link between industry and the creation of knowledge, the creation of improved exploration methodologies. And for 30 years, we've had this opportunity to work in partnership with industry and with collaborators like Geoscience BC to bring these things forward. So it really is a great opportunity today to help brag about some of the successes that we've had in this space. Dealing with these types of technologies, we really break them down into two parts. There's the predictive part, which is about fertility and trying to make upfront decisions. And then there's the detectability part, the detection, where some of these grains are actually recording the mineralizing processes themselves. And so I think it might be a good idea for everybody to have this sort of concept in their brain, that these are two different perspectives and there are two different scales of exploration targeting. These are not esoteric. They might appear to be because we're using things like lasers and we're talking about elements that are at the far end of the periodic table. But these are really tangible technologies. They're very easy to access through us because we have the access to the instruments. And so certainly the people who are listening to this, people that are reading our papers, the people who are members of MDRU can access these technologies very easily through us. And they are being applied throughout the world. There's some companies that have accepted this very boldly and are using it to lead their exploration approaches. We know from the work that we've done in British Columbia that companies have picked up on this and have used the data. We know that decisions to acquire ground have been made based on some of the information that you're going to hear today. And so we have a lot of confidence that these are the sort of types of information that maybe right now they're not in your toolkit, but we anticipate that they will probably be much more common to contribute to decision making in the next few years. Most of what you're going to hear today has been done and published, except for the last part. And Farhad will have a few slides at the end that indicate the work that we're doing right now on the advanced argillic regime. But it's a very similar approach in recognizing the detectable and predictable components within that. So without any further ado, I'm going to introduce Farhad. Farhad's been a research associate at MDRU for quite a while, and he really holds down a lot of our porphyry alteration decision making. He's an expert at recognizing trends and patterns and relationships within altered porphyry systems, and actually within alteration of any type, epithermal systems, orogenic gold systems. And he has an excellent way to ensure that context is brought forward, that we're looking at the materials and he's looking at the relationships between the materials and whatever geochemical data that come from that. So he really is highly skilled at ensuring that the information that we have has real rock context behind it. So Farhad, I'm going to leave it up to you.
Good morning, everybody, and thanks everybody for coming to this talk, and also I thank Krista and Craig for the introduction. Let me share my screen. So can everybody see my screen now? Is that right? Can you see, Craig? Okay, perfect. So I'll be talking about a summary, basically, of several projects that we did with the support of Geoscience BC during last several years. And I will be talking about Zircon, Apatite, and Titanite, and a few things that we are currently doing. And this work has been in collaboration with Craig Hart, Thomas Bissick, Antonio Salis, our past master student, and also Sean Barker at MDRU. First, I would like to thank Geoscience BC for collaboration and providing us the opportunity to undertake this research, as well as organizing this meeting. Okay, first about the porphyry deposits in British Columbia. Like any other part of the world, we have porphyry belts in British Columbia. And these porphyry belts, more pronounced than any part of the world, are associated with batholiths or various type of plutons. And you can see here, it's the map of South Central British Columbia, and you see the color one are various type of plutons that we have, and the lines indicates the different porphyry belts according to the Earth. So I don't want to go through in detail on these things, but most of the porphyry deposits occur within or around these plutons, batholiths, large bodies, and some of these are 50 kilometer by 50 kilometer. These are really large bodies. So let's look at one of these one, for example. This one at top is Tacom King batholith, and it has a porphyry type mineralization. So that's the map of that batholith up here. You can see most of the time these batholiths have several phases. And I'm showing here, so various color are different phases of the batholith, and I'm showing here basically example of the rocks, various rocks and units. Usually these batholiths start with a border phase, which is more mafic. You can see they have more mafic minerals, and they usually evolve to more slightly more felsic, more quartz monzonite bodies. The point here, if you look at this batholith here, so that's a scale 12 kilometers. It's almost 50 kilometer by 40 kilometer. The porphyry mineralization in this batholith is up here, within this body here. It's called wood jam area. It has several porphyry from alkalic to calc-alkalic type deposits. The main body of this batholith is this pink color, which is this unit, the Schoolhouse Lake unit. And this is the mineralized one, Wood Jam Creek. Texturally and mineralogically, these are very similar units. You look at the rocks, they are very similar. This might be a little bit coarser grain, but that's varies from place to place. The mineralization is not associated or does not occur, at least the big one, do not occur with this Schoolhouse Lake unit. The mineralization occurs with the Wood Jam Creek unit, which is a smaller body up here. So if you're an exploration geologist and you have a body like this, and your target is to find a porphyry deposit, which is the footprint of that exposed bottom is probably a couple of 100 meters only, and you have this ground and you want to explore for it, and you have a limited budget and time, where do you focus your exploration? If you know, based on some criteria, that this large body is not the one that carries porphyry type mineralization, at least economic one, then you can kind of not look at this and focus on unit on other ones. So if you know that this is the more prospective one, you basically spend exploration money on a smaller area, and probably it definitely increases your chance of discovery faster with less money. This is another example that, these are some of the areas that we did a study of that, and that's the Keyshawn Creek batholith. The same thing, it's a large batholith, 50 kilometers by 30 kilometers, and various phases of more mafic going to the slightly more felsic one. Bethlehem, Bethsaida, Eskina are the phase that carry porphyry mineralization, and there are a smaller body in the central part of the batholith, unlike the other one, which was as margin of the batholith. This one is at central part of the batholith. So the larger plutons are at the margin of this. In these units, they are not well mineralized. And the points here, various points here are actually areas that we went and did sampling for these things. And as Craig mentioned, and Krista also mentioned, these porphyry deposit in BC, you've got that's the porphyry belt here that we can see, and the red are the known porphyry prospects or deposits. And you can see there are a bunch of red spots here, and then they disappear and then appear again here. And that's largely because this central part around Prince George is covered by till sediments. So the porphyry covered mineralization continues, but the lack of exploration is largely because of the till sediments that they cover porphyry deposits. And these things could be a couple of meters only. So as long as you are standing above this and you have your traditional porphyry exploration tools, geochemistry, alteration, these things, is very hard actually to predict that you are standing on the top of the porphyry. So we were thinking what tools that we can develop to also help with exploration in these covered areas. So we come up with, we went back to the basic. So how can you make a porphyry deposit? So that's the batholith that I symmetrically draw here. And you can see it has various phases. And one of the phases is usually the one which has mineralization. And the other one, they don't have mineralization. And the reason that this one's been mineralized, because we know based on many research in porphyry deposit, if you want to make a porphyry deposit, you need some ingredient. You need water, metal, chlorine, and you need some sort of conditions, a specific condition from oxidation state, temperature, and pressure. If you put all these things together, then you will have a chance to make a porphyry within that body. So the idea of the fertility is that if we can look at these plutons and look at some specific minerals, can we identify that this body had these conditions? Therefore, it's prospective for porphyry, and the other one didn't. And we use minerals like this, various type of minerals, zircon, titanite, apatite, other minerals, to look for these things. So, and also, as Craig mentioned, these fluids, they make a porphyry deposit. That's a porphyry mineralization. And the process of making porphyry deposit mineralization creates a new set of minerals as a result of porphyry mineralization. And those are the minerals that indicate that the porphyry alteration has occurred. So those are the alteration indicator minerals. And their yellow cover here are the sediments or till or gravels, if you like. And these things erodes, and these minerals can be preserved because most of these minerals are resistant to weathering. So we can look at these things and look at the gravel and find these minerals and find if there is the host rock beneath these sediments are prospective for porphyry deposit mineralization. So that's the introduction. And how we did this, we went to all these various places, collected several samples, and collected minerals like zircon, apatite, titanite, and these are tools that we use, some of the tools. And some of the picture that you can see, we looked at these things by various tools, binocular and cathodoluminescence, which basically bombards the mineral with electron, and it creates the luminescence. And you can see this zircon grain here. You can see this nice detailed texture of the zircon using the cathodoluminescence imaging. And this grain here is apatite. And then we analyze this thing with various tools, microprobe, which is not shown here, and the UBC's PCIGAR, ICP-MS for trace elements. And then we looked at the trace element, but one of our goals was that we emphasized a lot of texture. We wanted to know how the chemistry of this point that we analyze, and the point we analyze is only 34 microns, and how these points, analyzed point, relates to the mineral, relates to the evolution of the mineral and the texture of the mineral. So we spend a lot of time characterizing the mineral itself before even start doing the trace element chemistry. And we find some interesting, very interesting result in terms of texture. So I'm showing today to you some of the trace element and textural relationship. So let's start with zircon. So zircon is a mineral, all you are familiar, is widely been used as a mineral for geochemistry dating with uranium lead. And people also use it for titanium activity as a thermometer and crystal fractionation and oxidation state of the mineral, of the magma. And as I mentioned, oxidation state is a key important feature for porphyry deposit. If your melt or magma has to be oxidized, the reduce, if it's reduced, you cannot make a porphyry. You need to have the oxidized. So that's why the zircon has been used, and it's shown by various previous study that you can use europium anomaly to measure the oxidation state of the parental magma. And this is what we basically did the same thing. And for the sake of this talk, I don't show all the sites. I just focus on two, which is Gishon Creek and Tacom Cane Batholith, the two that I showed to you, the geology. And here you can see the various points color are the various type of the Pluton phases, and the hotter color are the ones that are mineralized, and the smaller and cooler color are the less mineralized or barren. Same thing with Tacom cane. So Tacom cane, the wood jam is the mineralized one, the other one are not. And here I'm showing the europium anomaly in regard to hafnium, and hafnium is a measure for crystal fractionation. And you can see that in Gishon Creek, there is a trend more or less from high europium to lower europium anomaly. So you can see if the number is higher, about 0.3, 2.4 is more oxidized, you come here, is more less oxidized. And you can easily see that all the ones that are mineralized have europium anomaly consistently above 0.35. The other one have a scatter from high to low. Similar thing at Tacom Cane Batholith, you can see there is a spread of europium anomaly from high to low, and the wood jam creek is consistently high. But the other one, it's a Schoolhouse Lake, which I mentioned to you is the largest one, has similar European anomaly to the mineralized one. I explained, why is that? But the key point here is that we want to have higher European anomaly, which means more oxidized. But if we only look at one analysis, the high doesn't necessarily mean that's a good European anomaly, and that's my point. The trend is important because during the crystal fractionation, the European anomaly of the mineral zircons and will change from high to low. And that's basically an effect of crystal fractionation. What plays here is the importance of having this European anomaly high during the crystal fractionation. So the crystal fractionation effect do not basically change the European anomaly, because, and that's that things that makes these things is the water. So if your melt is wet enough, that high water content of the white mica depresses the feldspar crystallization and keeps the European anomaly high during the crystal fractionation. And that's exactly what we want. So in other words, having the European anomaly high enough, it's a sign of high oxidation, I said, but it's a sign of something which is even more important, in my opinion, that the magma was wet enough. And if the magma is dry, you never make porphyry, whatever what you want to think. You need to have wet magma, high concentration of water in the magma to make a porphyry deposit, because you need to make hydrothermal deposit. In other words, the European anomaly in zircon showing two things. The first is the oxidation state, but also, as pointed out by Dillis, it's a sign of how more water-rich magma. And the way that we look at these things, it's not the exact number, it's the pattern of the European anomaly. So if the European anomaly changes from high to low, is sharp like this, or it goes like this, in other words, it's less affected, the European anomaly of this yellow one is less affected to the crystal fractionation than the blue one, or something like to this, which is even less. So this one is more prospective than this one, and this one is more prospective than this one. So in other words, if you look at the average of European anomaly, this thing, they all may look like similar. What is more important is not the absolute European anomaly of single analysis, it's mostly the trend of European anomaly having that constantly high enough during the crystal fractionation. And that means both high oxidation state as well as sign evidence of the wet magma. Okay? We can look at the other things. I will very quickly go, and these things have been shown before, and the BC Pluton shows that exactly the same. That's the temperature thing. So you can measure the temperature of the magma using titanium and zircon. And here I plot them against hafnium. And you can see the non-mineralized one tend to have higher temperature, and the mineralized one have temperature below 750. And as it crystallizes, the temperature drops. And you can see even there is a trend from the Bethlehem to the Bethsaida, temperature constantly decreases, so that this one is less hot, if you like. And that's the temperature environment, the eutectic temperature environment, which is favorable for making the porphyry hardware deposit. At Takum Kimberlite, there are some units high, but there is a mix. So, some of the non-mineralized one and also having the lower temperature, which is similar to the mineralized. When you look at the various trace elements like this, yttrium to gadolinium, against thorium to uranium, and that's basically that trend. You can see a trend here, and that's basically a fractionation trend. You can see as you start from here, and as you more crystallize and you fractionate, you evolve the melt to this environment, lower tritium to uranium and higher yttrium to gadolinium, and that means more fractionated melt. And that's something you expected. You know, you start with a melt, it starts to crystallize and it starts fractionate and evolves and then makes a porphyry, and the melt that makes a porphyry mineralization. The point here is that you can see the differences between here at Gishon Creek with the one here. Both of them, you can see a trend around this curved path. And this curved path means a simple crystal fractionation. But you see these body that are highlighted here, that's that largest unit, a schoolhouse lake, which is not mineralized. And you can see all the points for that batholith, for that pollutant, are plotted off this curved trend. That the schoolhouse lake is not here. And it separates basically that pollutant from this mineralized one in this diagram. And there are people, various interpretation of this and why it is not along the simple fractionation trend. It's been suggested that these are mostly evidence of crustal mixing and contamination. So this melt has more crystal fractionation than, let's say, the wood jam creek. That's the interpretation. I think that's a fair interpretation. So in other words, if you're looking at the crystal fractionation, you want your body, your pollutant, have a simple crystal fractionation. If anything is scattered, that's not good for various reasons, and probably more due to the crustal contamination and mixing. So you want your body to be around this curved path. Okay, now let's look at the texture as I promised. So we looked at the texture of the zircon, and these are some of the texture that you see. It's very common. You've seen this in concentric oscillatory zoning in zircon. It's very common. Zircons that usually have a more fat texture, but we also saw some zircons that are elongated. And when you look at the CL of this thing, cathodoluminescence feature of this thing, they show this kind of tabular zoning. So we started to see, okay, what does this various texture mean? So we started to characterize these things and classify them. So we could easily classify zircon into tabular or oscillatory zoning. What we saw a texture, which is a kind of crossover between these two, and we call it tabular and oscillatory zoning. And you can see they start to be tabular and then evolves to have this oscillatory zoning. And that's exactly the term means. The other type of texture that we saw, it was, you know, I couldn't find a better word, but they show very irregular texture. For this zircon here, you can see it has nice, perfect, nice oscillatory zoning. But suddenly something happened. The texture become very irregular. You can see it looks like a xenocrystal has been fused into the zircon crystal, and looks like something like it's been melted, or the original oscillatory zoning has been destroyed and make that feature. And at the end of the crystal zircon crystallization, it started to repair itself and back to the concentric zoning. And this one is even more. You can see the core of the zircon usually have this kind of black feature. It's kind of on the side, and the zircon texture is very irregular. So the detail of this and why they are like this, it's a lot of people can discuss these things, but we kind of empirically we classify them as irregular. That's the easiest thing that they could see. So these are kind of 4 type of the main zircon texture that we see. So how does this texture relate to the composition of the zircon? So we tried to do the same thing for the sample europium anomaly, like regarding the hafnium that we saw before, which was a sign of oxidation state. And I'm plotting here different textures. So the red circle are the oscillatory zoning, and the blue signed are the tabular, and the green are the tabular oscillatory, those crossover texture. You can see there is definitely overlap between these two, but there is a clear differences that you can see. Most of the tabular and oscillatory tabular are the ones that have lower europium anomaly, And the one with oscillatory zoning most of them tend to have higher European anomaly. So in other words, you can look at the texture of this thing and kind of predict, at least on average, which unit has more tendency to have higher oxidation state, even before doing any type of analysis, just looking at the zircon texture. And this one, I'm plotting this thing against the age, the same thing here, European anomaly is against the age. You can see the one that have more oscillatory zoning, higher European anomaly, and is slightly younger than, on average, than the one that we tabular. And that's basically what we saw. We always saw the oscillatory zoning, it starts with tabular and goes to oscillatory zoning. We never saw the vice versa. So it means that this tabular zoning it starts at the beginning of the crystallization and then evolves to more oscillatory zoning. And that's basically works with what we already know in terms of temperature. You start something with higher temperature, and probably at that environment you form tabula, and then the temperature drops below the eutectic and you start to having the more oscillatory zoning, and that's where you get the porphyry copper deposit mineralization. So based on the zircon texture, you can kind of guesstimate the temperature as well. So in other words, if you're looking, also I forgot to mention about the irregular one. So you can see we have the one that have irregular texture. How does one relate? Here, I'm showing only for Gishu and Craig. You can see it's a kind of a spread, and they start from high European anomaly to low European anomaly. And these are the one with more oscillatory zoning, and there is from high, some of them low as well. But the one with oscillatory zoning tend to have more hafnium concentration, and that's again means that these are more fractionated relative to the one with irregular zoning. So in other words, if you're looking for the porphyry deposit, if you're looking at the zircon only texture, you want to have zircon with oscillatory zoning, and particularly those with the regular zoning. The irregular zoning, is it the high effect of temperature or various reasons that can be discussed, are not even are less prospective than oscillatory. Just simple oscillatory zoning zircon is best. Okay, that's what's good enough about the zircon. Now let's look at the apatite. So apatite, we can learn a lot of things about zircon, but apatite can give us something more, something that we cannot see in zircon. And that's the clue about the sulfur and chlorine in the magma. And as John Dillis and other researchers pointed out, porphyry deposits are actually sulfur deposits. So you have a lot of sulfur in porphyry deposits. And in fact, the porphyry deposit, relative to the average crust, have lower sulfur to copper ratios. So here, John Dillis kind of averages these things. So in crust, you have 1 to 5 to 10, and in porphyry deposit like El Salvador is 1 to 100. So sulfur is very key important for mineralization. So if the magma doesn't have sulfur, it doesn't make porphyry mineralization, as well as chlorine. Chlorine is also important because it carries the copper and to the hydrothermal fluids for making the porphyry deposit. And apatite, first of all, has chlorine, and because of its structure, it has a lot of trace element in it, so including sulfur. So we can look at the sulfur and chlorine evolution of the melt, parental melt in our Pluton. So I showed you some images of using the cathodoluminescence. So if you haven't used cathodoluminescences, it's a fantastic tool. And this is a transmitted light image of a thin section. There is feldspar, apatite, various type of minerals here. And this is the image, same thin section with Cl. You can see much detailed texture because everything is like color. And you can see various type of minerals, feldspars, apatite, various type of, so feldspar, here it's apatite, and here is the magnetite with inclusions of apatite. So this is from my picture when I was grad student in the previous century. So I was looking at these things, and I knew that the Cl is very good for apatite. So when we started the project with geoscience species, that was the first thing I did. I put these grains under the Cl, and we saw this texture. So apatite was not zoned. We can see apatite grain here are zoned, and they have different luminescence color, basically. And here you can see it starts with a little bit brownish, goes to a band of more brown and then less brown. Same thing here. The core is a little bit brown and less brown. And you can see nice urethral apatite grain and goes to brown. So there was some zoning with various luminescence, and we were thinking, what are these? So the easiest thing was to put them under the electron probe and analyze them for sulfur and chlorine and a bunch of other trace elements. And this is exactly what we did. We analyzed all these various zones, and we find that the exact cause of the luminescence, could be very complex, but the various luminescence color correlates with sulfur and chlorine. So the one that have more brown luminescence tend to have higher and sulfur chlorine. This one, that sulfur drops, but it still has higher chlorine. And then, so number 2 has less sulfur and chlorine, and that you come to the rim, which has the lowest sulfur and chlorine, and it has also a little bit more greenish luminescence. So the apatite is not homogeneous; it's zoned. Apatite has sulfur and chlorine. Then the sulfur chlorine of the apatite is higher in the core, and as you come to the rim, it becomes depleted in sulfur and chlorine. Okay, so that's what we learned from this various thing, and then we kind of analyzed a lot of grains. So this one shows at Gishon Creek battery. And again, the hotter color are the mineralized one, and the other one are not mineralized. And I'm looking at the sulfur against chlorine concentration as per formula unit. You can see, strangely, the mineralized one has the lowest sulfur and chlorine. So most of the grain that we apatite at Gishon Creek have the lowest sulfur and chlorine concentration. The other one have concentration from high to low. So at the beginning, I thought, I liked it the other way. I liked that the mineralized one have a higher sulfur and chlorine, but this is exactly what caused this Gishon, the Bethsaida to the porphyry-rich mineralization, because it has lower sulfur and chlorine, because sulfur and chlorine is depleted in the magma to make the porphyry deposit. And basically, the leftover, the apatite that formed from that leftover melt are having depleted in sulfur and chlorine. So in other words, still we know that in most of these mineralized batholith, there are apatite that they have signs of core. So you still want to see apatite with core, which has higher sulfur and chlorine. That means the melt had originally high sulfur and chlorine. But then you want to see a lot of apatite, which are depleted in sulfur and chlorine. That means the whatever magma was there has lost all its sulfur chlorine somewhere, and that somewhere is hopefully your porphyry copper deposit. So you can see the sulfur and chlorine evolution and use that as a sign for fertility. And if you look at the luminescence of these things, if you don't want to do the probe analysis, you can use it, and I kind of colored them based on the color. You can see the one that the brown one tend to have higher sulfur and chlorine, and the green one are the one that have lower sulfur and chlorine, and that's the one which is mineral. Okay, the last mineral is titanite. We looked at the titanite. The titanite doesn't show very much under the Cl. You can see some sort of zoning and thing under the SCM, and this is a SCM of the titanite. And titanite also can have a lot of trace element. The good thing about titanite is that if your Pluton has titanite in it, it means that the magma had enough water in it for porphyry deposit. And that's because of this equation that I'm here, that the pyroxene with ilmenite quartz, if you put a little bit water on it, you can form titanite and hornblende. So titanite is very common in hornblende rich rock, okay? So, and you know, if you have hornblende, that means the magma was wet. So just by having titanite, a lot of titanite in your gluton, that means wet magma. So that's the pure mineralogy. But what we did, we analyzed these things and we looked at several things. One thing that I realized it's working very well, that's iron to aluminum ratio. And the iron to aluminum ratio in titanite, based on published research, is an effect of oxidation. So more oxidized environment, in a more oxidized environment, the iron to aluminum ratio in titanite goes higher. And when we did this, we saw exactly the same thing. The mineralized one have titanite with higher iron to aluminum ratio. Same thing at Takumken, you can see the mineralized one had higher aluminum to iron ratio. So this is if you like another way. If you don't like, or if you want to have another, you can use the europium anomaly in zircon to measure the oxidation state, but you can use titanite as well. And in fact, I think titanite works even better. You remember from the europium anomaly in zircon, it could not separate the wood jam from a schoolhouse lake unit. But here, with the titanite in apatite, you can see it separates these two units very nicely. So that's, in my opinion, titanite even works better for having the oxidation state of the magma than zircon. So just to conclude, we also, so these were all things that Craig mentioned. These are all about the fertility. We can look at the titanite, apatite, and zircon to identify which melt had the condition for fertility. But we can use same type of minerals to have evidence of alteration. In other words, evidence that the hydrothermal fluid was there and it made the rock alter it. So we're basically looking at alteration. And if you are a porphyry geologist, you like to see the alteration and vein, all these sort of things. That has worked very well in exploration, all these alteration zones. But if you don't have the rock, or the rock is heavily altered, all these minerals are destroyed during the alteration. But there are a bunch of minerals that can persist during an alteration. And even though the main alteration assemblages is destroyed, we can look at some of these minerals and have some evidence about the alteration. So we looked at these things, we went back to look at the apatite. So is there any evidence in apatite about the alteration in porphyry deposit? And the answer is yes. You can see the alteration in apatite. And these two images are from Huckleberry and Highland Valley apatite. It can show this uniform, the typical concentric zoning in the apatite that you can see. And the luminescence of the apatite can change from yellow to brown depending on the type of pluton you have. It's more in alkalic deposit. You tend to have this. In calc-alkali, it could be more yellowish. So these are the example in the case selected altered. So that's from Mount Poly. You can see nice zone apatite has a rim of green luminescent secondary apatite formed during the alteration. So these are the apatite forming as a result of potassic alteration. The potassic alteration also changes the composition of the apatite. And you can see the apatite here at Highland Valley was originally yellow. It's now has this distinct greenish color. Okay, so that's the effect of the potassic alteration, changes the luminescence of the apatite. But you can see here something else. You can see some luminescence has been destroyed. You can see this gray luminescence. So that's the overprinting phyllic alteration. So if you like, my apatite grain had that yellow luminescence originally, have been potassically altered. I have this grain luminescence, and then overprinted by this gray luminescence, or destroying the luminescence as a result of phyllic alteration. And in this grain, looks like it went back to potassic a little bit more green luminescence mantling afterward as well. If you have more intense phyllic alteration, this is what happens to apatite. So this is the apatite grain on the SEM image. You can see there is not much zoning. You can see this sulfide here. There's a tiny fracture here, so it has deposited pyrite and chalcopyrite, a little bit pyrite here. This is the image of apatite of the same grain under the seal. You can see far more detailed texture of the apatite. And you can see here, the apatite, all the green, yellow luminescence original have been gone, been altered to, all the yellow luminescence is gone, have been altered to this green luminescence as a result of potassic alteration, and then destroyed the luminescence to this gray one as a result of actually fluid passing through this tiny fracture here, depositing a little bit sulfide and destroying the luminescence. So this is in fact a phylically altered apatite. So it's exactly the same thing if you pick up a rock in your hand and look at and say, okay, this rock has sericitic alteration. I can look at the same grain on apatite and have the same conclusion. And if you do analyze these things, the chemistry of these things are different. The apatite in fresh rock has yellow luminescence, higher rare earth elements, and manganese to iron ratio. You case liquid alterate has the green luminescence with lower, and then the phyllic alteration, basically you lose all the trace elements. So phyllic alteration, because of the acid environment, it removes a lot of trace element, destroying the seal of the apatite. So that's basically using the composition. But more easily, you can look at the apatite, just look at the luminescence color of the apatite and see if the apatite is coming from the porphyry deposit, making that alteration. And finally, you can do the same thing with apatite. This is a study from Antonio Solis. He looked at the titanite. Titanite could have different color texture, and the titanite, as a result of alteration, changes its color, goes to more secondary blonde and dark brown color, and that's mostly because you start to form rutile after the alteration of titanite, and then we analyze these things. The trace element of the titanite also varies. And this study was specifically for alkalic deposits. You can see the rare earth element, as you think alteration decreases, the iron to aluminum ratio increases more significantly than we did, and I'll show you for the original magmatic oxidation. So these things have very high iron to aluminum ratio, and the vanadium also decreases. So you can classify the titanite based on the texture and composition as a sign of alteration. So to conclude, so when you look at these things, you have a large battery, you can do a couple of, it's common to analyze, to date some of these pollutants, but nowadays, if you send your sample to age dating, more or less with the same cost, you can analyze for trace element as well. And you can get a lot of information regarding the fertility of these things. So for zircon, you can look at the texture. We were looking for zircon with oscillatory zoning and the simple crystal fractionation. You can look at the zircon titanium in zircon temperature and find evidence of the temperature of your parental malt. You can use the European anomaly to estimate the oxidation stage. With apatite, you can get more information about the sulfur and chlorine. So we are looking at the apatite with evidence of high sulfur and chlorine, but largely depleted at rim. And with titanite, you can get another evidence for higher oxidation using the iron to aluminum ratio. And for alteration, you can use the luminescence of the apatite based on the color and trace elements to see how the trace element evolved in the apatite as a result of alteration. Is mostly losing a lot of trace elements. And same thing with titanite, you can use the color of the titanite texture and also its composition, particularly rare earth element, vanadium and iron, aluminum, to basically classify the titanite associated with porphyry alteration. So these were things that we did with Geoscience BC regarding the fertility and identifying the alteration. Actually, without having a rock in your hand. but you can collect some minerals and you can get a lot of information. We did so basically using that, you probably find a prospect, but we went another step forward. So you have a prospect, you have an area, you want to vector towards that prospective area that you find using these tools, and you want to vector towards the porphyry deposit at depth. So we also, with the help of Geoscience PC, we did a little bit research on these things. So this was a research that we did at Titanite area, and we looked to develop some techniques for vectoring toward porphyry. And this was one of the first projects we did on Titanite. And we kind of developed some sort of alteration indices, also using the whole rock geochemistry for acid digestion techniques. And here I'm looking at this ratio, which basically we comparing the elements that occur at the bottom of the porphyry relative to elements that occur in the upper part of the porphyry, and we kind of develop this ratio, MDRU porphyry index or MPIX, and that can be used as a very good sensitive method to basically measure the distance, the approximate, the relative, not the absolute, relative distance to a porphyry type mineralization. So that's been published by Geoscience PC in our Titanite project. It worked very well, and based on I've heard from industry, from several other persons, they had very good results using these indices as well. And currently, we are doing more work on the vectoring techniques using various mineralogical and geochemical tools. So we want to have a better toolbox for exploration when they have a bunch of alteration, altered rocks and some whole rock geochemical data, and they want to vector towards the porphyry. So we are trying to improve that toolbox and techniques. So we looked at the advanced argillic alteration. So in other words, the alteration at the shallow part of the porphyries. And this is one of the sites we looked at, the Tanzila main, which is more advanced argillic alteration. Below it, and this at the far distance from it, this is a monzonite with potassic alteration. So we want to use the technique to vectors toward the mineralization. And we are using various techniques like at the cathodoluminescence. So we are looking at quartz, these beautiful red luminescence quartz, which means a lot of things. So, and also we are looking to develop new techniques and new indices for vectoring. For example, here I'm looking at sodium calcium. So these are the current research we are doing, and we will be publishing some of the preliminary results in the summary activities in a couple of months with Geoscience PC, and you can find some information about this. And that's basically all I had for today. If you would like to read more about these things, most of these things have been released by Geoscience PC or published somewhere else. And this is a list of publications that you can go and read with some links to the reports or paper that are available online for your interest. Thank you very much, and I appreciate it for your time. And I'm now open for if anybody has a question, if I can answer them. Thank you.
Thanks, everyone. Yeah, we actually have a question for you from Taylor Farhad.
Yes.
I'm just going to pull that up here. It says, in your figures with the different textures of zircon with europium, age and hafnium content, the tabular zircons are older and have higher hafnium. If hafnium increases with fractional crystallization, wouldn't you expect older zircons to be less fractionated and have lower HF and younger grains to be more fractional? Could the less fraction younger zircons indicate mafic magma recharge?
It's, there is a, it's relative, but there is a, each of them, you can look, there is a trend from higher hafnium to lower hafnium. So each of these melts start from higher temperature to lower temperature. So these are each, if you like, each of these batholiths, they evolve through that pattern of the crystal fractionation. And it could be, some of the, as you said, some of the Complexity in the magma injection of the mafic melt also contributed to that as well. That's possible, yes.
Okay, we've got another question here, Farhad, from Lewis here. In case ICP mineral chemistry is not available, would it be useful to use EMP instead of ICP?
Well, in fact, for apatite, yes, because we did for sulfur and chlorine and titanite as well for iron to aluminum. So you can do most of these things with electron probe microanalysis. But for other trace element, rare earth elements, you need to have ICP-MS. So that's unfortunately cannot be done by microprobe. For some of them, yes, but for trace element like rare earth elements, you need to have ICP-MS.
Okay, great. The last question that I have so far is, second last. Just looking at, it was shown the sulfide inclusion in apatite. Have you seen the sulfide inclusion in zircons?
Sulfide inclusions in zircons, not very common. No, I haven't seen sulfide inclusion in zircons. No, not very common.
Yeah, so Farhad, just curious, you've done a lot of work in this. Where do you see this research going? And sorry, that's my dog in the background. And the progress. Maybe you can expand on sort of the next step on this research.
Well, I mean, that's an important question. The more fundamental question here is that the alteration is rather simple and straightforward. You find the evidence that a rock has evidence of alteration, but the fertility, the question that you probably would ask, what does it mean actually, the fertility? We kind of borrowed this from biology. So in biology, the term fertility used, you can as a sign that somebody is either fertile or not fertile. Yes. So, but in geology, you could be in between. So you could be fertile and not fertile, and so in between, which is not possible in human beings. So we kind of use the fertility things as an indication of how good is that thing for mineralization. Okay. So yes, exploration companies wants to have something fertile, but how good is that fertile? Is it the so-so fertile, or is it the good, really fertile, making a giant deposits? Okay. So most of the things that has been done in the PEMS environment so far has been focused on finding, is it fertile? And that fertile includes the so-so fertile as well. Okay. So the way that we would like to advance this, we want to have better indication to separate the so-so fertile from the good fertile as well. So in other words, we would like to have more evidence that, and that's, I agree, I'm sure that a lot of you agree, that's a very important thing, but that's also very challenging environment as well. But there are probably some evidence, some things that we can do to make that distinction, even if not very good, but at least an approximate indication that we can separate these two is very important for exploration companies as well. So that's where I like to see the move of the porphyry indicator minerals, not only the characterizing the fertile and not fertile, but also trying to rank different type of fertility as well. So the one that are more, if you like, fertile for having larger deposits and the smaller deposits.
Great. Yeah. And just for the audience here, we didn't have a poll question, and just out of curiosity for our sort of data capture. If this sort of topic applies to your exploration program, feel free to just in your chat put yes, and just so that for us to know, just for our interest. In terms of the last few questions we have, just looking at Cole here.
Well, your dog has a question.
He wants to partake in this. Have you been able to relate these minerals, i.e. zircon, apatite, to the economics aspect of the mineral deposit?
Well, that's what exactly I kind of answered for it, and that's, as I said, that's a really excellent and important question. I mean, you know, when I talk, you know, about the porphyry deposits, we remember that diagram I showed you about the ingredients and condition you want. So I mean, the porphyry deposit, it goes back to that how efficient were those criteria, all of them. And you know, maybe I have to kind of say a little bit things that I'm thinking. So if you let's say you have 5 criteria, you study 5 criteria, look at the temperature, look at oxidation stage, look at sulfur, uranium, you look at in your prospective area, you look at several things in zircon, apatite, and titanite. The one pluton that has satisfied more of these criteria is better than the one that has less. So if you have 4 and the other pluton has 3 and the other one has only 1, which is oxidation state, definitely the one which has 5 of these criteria probably has better in the potential for having a more economic porphyry deposit. So, but you know, we would like to do better than that. But I think they're very, at least with the current information that we have, current knowledge that we have, we want to see more. And that's why I like to emphasize that if you only look at zircon, you get some of the criteria. But if you look at titanite, apatite, and more minerals, more criteria, and if the pluton satisfies more of the criteria, that means something. And that's important. So we would like to see more of these things in a mineralized pluton. And that's probably depends on the economic or higher potential for hosting porphyry mineralization. I don't know if Craig has a comment on this or not, because that might be something very important.
No, I think you got it right on, Farhad, is that really everything that we're doing here is we're developing a whole bunch of tools, and we hope to bring these tools together in a tool kit. And some of these are going to work and we can use them and modify them, and other ones that won't work and we'll drop them off. But, you know, from one rock, we can apply almost everything that Farhad has mentioned here, or from one till sample, or from one regolith sample, or from one stream sediment heavy concentrate. And so there's a lot of information that we could pull together that would help inform decision making, but ultimately it's going to come down to a ranking, and we're going to pull those tools together that we know that work for that belt or that arc. And as Farhad says, it becomes a bit of a numbers game in terms of how many of the positive indicators are working. And a lot of times we don't want to get all the way to a laser to get this ICP chemistry. We're looking for proxies. Maybe there are things in the whole rock response. Maybe there are things that are just by looking at the grains, we can tell already. So I think we're just trying to find ways to be more efficient to bring that tick mark into your toolkit to give you a ranking to contribute to decision making.
Actually, there's a few more. I'm going to jump around a little bit because I can see a lot of people are wanting the application for, in terms of zircon geochemistry, is it possible to use the C ratio from discriminate barren and fertiles?
Can you say that again?
Sorry, in terms of zircon geochemistry, is it possible to use the CE ratio from?
Oh, certainly.
Yeah.
Yes. Well, depending on what method of trace element analysis you want to use, the instrument that we have at the to measure the serum anomaly, some of the trace elements that you use were used for that calculating the cerulean anomaly. They are usually have very low concentration in zircon. So you need to have a method for making those analyses inaccurate. With the one that we have at the UBC, because it's a very low concentration, it's very difficult to get to that concentration for those specific elements. So that's usually a challenge for making the cerulean anomaly measurements in zircon. But if other techniques, which probably a little bit more expensive and more time consuming, you can do that, yes. If you can get analyzed for in lower detection limit for those trace elements.
Okay, great stuff. In terms of collecting the samples and QA/QC, in terms of protocol and things, do you mind just maybe, sort of sharing what they may be in terms of collecting the work?
Well, yes, we have the standards, and then we kind of when we analyze the thing, so we always try to do one of the reasons we do the petrography to find, because the zircon apatite could have inclusion, fluid inclusions, all these sort of things that may affect our analysis. We do a lot of background checks to make sure that the point that we're analyzing represent what. And then we have a series of techniques looking various trace element concentration to see if the analysis is acceptable or not. For example, if it has higher lithium, if you are analyzing for zircon, higher phosphorus things, so we know that there is a contamination. So we have a lot. Usually when you do these things, you try to analyze a lot of points, and then you look at them and you discard the one that had any type of contamination, or that for any reason the analysis is not acceptable. So some of these things, have been discussed. If you look at some of my publication, or Robri also are trace element zircon expert at the UBC, he has done protocol for these things. So if you look at some of his publication, these things have been discussed in detail there. Yes, we always do quality check after we do analysis.
Yeah, and before I jump over to an audience asking a question, the last one I have here is, could the discriminant diagram may use in other types of deposits?
Potentially, yes. I mean, it depends, what type of deposit it is. But if most of these things, because the porphyry deposit, the good thing with porphyry deposit is that they have very, very clear and obvious links to the magma. And some of the other deposits, the link may not be as strong as what we know about the porphyry deposit. So if you're looking at the fertility thing, so there might be some need to be modification. So you need to exactly how that deposit form, and then you look for that as specific criteria in that environment. But for alteration, yes, you can see what type of resistant mineral is there, and you can kind of look for evidence of alteration that occurred to those minerals. It's pretty much the same principle. So it depends, I'm not expert in other deposits, but I assume that if an expert in VMS or orogenic gold or other environment, you can get some useful information as well in that environment.
Thanks, Farhad. I'm going to open this up to Jonathan. I know that he's got a question here, but we want to hear from you. It's been a while. Jonathan?
Jonathan, are you in Australia still?
Yes, I am. It's a ridiculous o'clock in the morning here, but thank you very much for the presentation. It's really informative. It's really nice to see a synthesis of all the work that's been put in over a number of years by you guys that we've been following in Australia in the porphyry exploration space as well. So thank you very much for the presentation. The question I've got is mostly about the application to exploration on the ground once you've established the fertility of an area, in terms of what we've discussed in terms of Titanite and Zircon and Apatite. I'm wondering whether or not there's been any evidence or work done on quantitative mineralogy around the relative proportions or abundance of the different types of apatite that you're seeing in the systems above the mineralization and compared to the cores, and whether or not you see any zonation in that respect. And also, just a sort of a follow on from that, do you see any association with other rare earth element bearing phases in the more prospective environments that you're not seeing in the more barren or the non-ore forming environments? I'm thinking about monazites and things like that at the moment. It's just some trends that we're picking up in the lock and fold belt in our porphyry systems, and I'm just wondering whether or not that's bearing out across the systems in British Columbia as well.
Well, I think that's an excellent question. What we did so far, it was mainly looking to see in terms of fertility, if is it fertile or not, less fertile or not fertile. So we haven't done a more detailed study to see, let's say, if you are at base zeta, if there is a vectoring within the apatite as you get closer. And I think that's a very important. I think that would be excellent study if somebody or us can undertake. So that's we haven't done it, so I cannot answer specifically for fertility. But what I can tell you, what we realized, that as you get closer to the porphyry mineralization, not in zircon, because zircon is very resistant to hydrothermal alteration, but in apatite, we could see some changes. So even the rocks that are several kilometers away from the porphyry, if you look at my diagram of the alteration, so the apatite is very yellow, very distal, let's say 6 or 7 kilometers. But as we get closer to the porphyry, even though the rock was quite fresh, we could see a little bit of sniff of the alteration on apatite. The luminescence of the apatite become yellowish green, and then it start to see more of the greenish potassic alteration. So we could see a trend of seeing that hydrothermal fluid. So in other words, the distal footprint, alteration footprint, yes, I can tell you that we could see that. But for fertility, we haven't done work, and there might be something, forming. The other thing that I would like to mention, some of these things in terms of fertility things. So we looked at the main phases, but in a lot of environments, there are dikes or bodies that they cut the porphyry. So they are post-mineralization. And if you look at some of Rob Lee's more recent publication, he also describes some of the, in terms of timing, that we look at the plutons that occurred before, during, and after the mineralization to look at the fertility signature of these things during this time.
Excellent.
I don't know if Rob Lee is around and if he wants to comment on this, because he has done excellent work on
yeah, I think Rob was. He was partaking just a bit earlier. He just signed off.
Okay, sure. I don't know. That's what I think. Yeah.
Yeah. Before we close here, John, hopefully we answered your question. Craig, you've got a moment. You want to talk a little bit about commercial?
Oh, just I know a lot of the questions were about, well, actually, how do we get this stuff done? And so when people are thinking, how can I apply it to my project or my property? As I say, we've got the capacity to do all this stuff within MDRU, and we can do this commercially for our MDRU members, but we really are more looking for research opportunities to test these things out, to do scoping studies, to do proof of concept studies, to try and find out ways and means to apply these sort of technologies to different parts of the world. So I think we're very much open to trying to find some way to establish partnerships and relationships with a number of companies to try and show some increased applications. And certainly even within British Columbia, we got great support from Geoscience BC, but we know that there are more detailed approaches that industry want to consider. And so I just want to throw that out there that, you know, don't hesitate to contact Farhad, myself, or anyone else at MDRU.
Great, thanks, Craig. Thanks, Farhad. Well,
No
with that
worries.
said, you know, it's 11:17. I'm gonna close the session. I want to thank Geoscience BC, Krista, Rich, and Candace for helping us and co-chairing this session. It's been a great turnout, and this session is recorded, so we'll make sure that it's on the Geoscience BC YouTube channel, and it will also be funneled through the MDRU YouTube channel as well. And I echo Kylie's comment there. You know, Farhad, it's been great to have this session, and your research and your passion really shines through. Yeah, it's phenomenal to always host these sessions and do a little bit of show and tell. For all those who's sticking around, our next Zoom with MDRU session is in November, so stay tuned for more information. I'm going to close here officially. Thank you everyone for joining. Have a great morning, afternoon, and evening for wherever you are. Take care.
Turn your camera on and wave goodbye.